All right, everybody, I'm going to now walk through three examples that correspond to the types of homework questions that you have for Chapter 5. We're going to do one single-dimensional example, two-dimensional examples, and then lastly, I'm going to do a cut point example. And I can't do full screen, but I think I can screen share still with Keynote here. So let me do that, and then you guys who are here can tell me if it's coming through. So give me a thumbs up or say something in the chat if I can get the chat back. Just to let me know if you can see the examples slides. Is that coming through? Or is it still just me? I saw your mute go off, but I didn't hear anything.
It's coming through.
Okay, thank you, sorry. Next to the post office is actually sometimes really loud with the trucks, so. All right, okay, so here's Chapter 5. So the first one I'm gonna do is this example. Legislature with 5 members who each have an ideal point in the policy space. The policy space is 0 to 80. I often use 0 to 80 because it's much easier to freehand a graph that is 0 to 80 because you can always cut it in half, right? You can draw a line pretty much eyeballing it at 40, and then you can go 0 to 40 and eyeball 20. And if you go 0 to 100, you get into decimals really quickly. So 0 to 80, 0 to 800, 0 to 8 are ones I commonly use. Each legislator has preferences that are complete, transitive, single peaked, and symmetric. Complete and transitive, that's from that we always use more or less in these kind of rational choice or economic models. Single peaked means that utility function has one peak, and then symmetric means that as you move away from their ideal point, their utility falls the same, no matter which direction. So what that lets us do is get rid of the utility dimension. We only have to draw the single issue dimension. So for a single issue dimension model, it'll be a number line, all right? So here we have 5 people: David Bazan, Patty with 1 Y, Griffin, Elliott Smith, Phoebe Bridgers, Nick Drake, and the status quo is currently at 40. And if at any time somebody has a question, just pop on your mic or throw something in the chat and I'll try to keep my eye on it, all right? Let me make it bigger there so I can see it. So you may want to even take a screenshot of this real quick and have it off to the side as I'm going through this, because I don't have these numbers written out on the graph, and it's not going to work the way I thought. I'm going to try to do full screen because I took some time to make it where it builds in. So let's see if this works. All right. If this doesn't work, you have to tell me in the chat or over microphone because everything else is hidden for me. But hopefully this works. All right. So here is our example. And then here is the model. So I've put everybody where they go. Hopefully I got that right. David Bazan at 25, Patty Griffin at 35, Elliott Smith at 45, Phoebe Bridgers at 50, and lastly, Nick Drake at 60, and the status quo is at 40, all right? Now, this is just drawn in this is Keynote, but like PowerPoint, so it's not, I didn't type in the values, so you can see there's just a little bit, it's not perfect, but it's pretty close. For the homeworks and exams, I use a program that's a little more precise, but for just this explanation, this is sort of me freehanding it, but with the tools available in the slideshow software. So the first thing I want to do is I want to draw everyone's preferred 2 sets. Now, I didn't have to put in the utility dimension here because I know that David Bazan's utility, all that matters is the distance from his ideal point. So in other words, he is indifferent between 30 and 20. We wouldn't know what he would vote for if we offered him a vote between 20 and 30. All right, he would just flip a coin or something. But we definitely know he likes 29 compared to 20. 29 is closer. That means if we were drawing that utility function, it would be higher on that utility dimension. So by assuming single-peaked and symmetric preferences, we're able to not have to draw that dimension. It doesn't mean it's not there, but it just means we know what it looks like so well that all we have to worry about is the Cartesian distance, which is just plain old distance that you know from most math classes, distance on the line. So here at 25, this distance is 5, this distance is 5, so he likes those things the same. He is indifferent. Those would be his indifference points for 20 and or 30. But we're worried about 40 here. And so I accidentally clicked, and so we've already seen here that this is his preferred to set. And again, it's not quite centered. Now that it's blown up, I can see I missed it by just a little bit. It should be centered on his ideal point. And then he definitely likes everything between 40 and 25 because we're getting closer to his ideal point. But because his utility function is single-peaked and symmetric, we know he likes everything also between 10 and 25, all right? So what you do is you find the point that we're comparing, then you find his indifference point. So he's indifferent between 10 and 40, and then everything inside of those two indifference points is his preferred to set. He strictly prefers everything between 10 and 40. But 10 and 40 are not in the preferred to set. He does not prefer 10 to 40. He doesn't prefer 40 to 40. They're the boundaries of the preferred to set. So that's why we have these weak brackets or parentheses here, all right? So the preferred to set of David Bazan, that's a subscript, although it's capital letters, so it doesn't look like a subscript. It is, it's a subscript of the alternative 40. You could also write SQ here if you wanted, is 10 to 40, all right? So any questions on just that part of drawing the preferred to set? And I'm gonna see if I can center this up a little better while I wait. Oh, I've grouped it. So let's see if I can get it a little bit closer to where I want it. It'll change when I blow it up. All the little tiny errors are magnified. And somehow I got rid of this. What's going on? Oh, well, it's doing that. Okay. All right. Now, let me go back here. Okay, so no questions on his preferred to set. Oh, I need to regroup that. That's all right. So next is, not Anna, Patty Griffin. There we go. Go ahead while I'm here and regroup these. Okay, Patty Griffin. So her preferred to set is everything between 30 and 40. I'm sorry, 35 and 40. Her ideal point is 35. Definitely, right? Because moving this direction, we're getting closer to her ideal point. She definitely likes them better. But because her utility function is single-peaked and symmetric, she also likes everything between 35 and 30 the same. First, I found the point I'm comparing. Her indifference point is 30. Everything in between 30 and 40, she strictly prefers to 40. She doesn't prefer 40 to 40. She doesn't prefer 30 to 30. That's why they get soft brackets instead of hard brackets. In set notation, this means that number at the end of the interval is not in the thing we're talking about. It is the boundary of the thing we're talking about. So 29.99999999999 repeating is in the preferred to set, but 30 is not, all right? Same thing here, 39.9 repeating is in the preferred to set, but 40 is not, it is the boundary. So there's Patty Griffin's preferred to set. Elliott Smith, he likes everything between 40 and 45 because we're moving toward his ideal point, right? And because he has single peaked and symmetric utility, he also likes everything between 45 and 50. 40 and 50 are the same distance from his ideal point. Those are his indifference points. They're his indifference points for 40, which is the status quo. So everything between those two is strictly preferred to 40. All right. Same thing with Phoebe Bridgers here. She definitely likes everything between 40 and 50. Why? Because if I had drawn her utility function, all those things would give us higher utility numbers, right? We don't have to draw that utility function, but we always have to remember it's there. That's why she strictly prefers everything between 40 and 50, because they give her more utility, all right? And because she has single peaked and symmetric utility, so what is she indifferent to with respect to 40? Well, 40 to 50 is 10, so go 10 more in the other direction, that's 60. So 60 is also an indifference point, and so those are the boundaries of her preferred to set. They're not in the preferred to set, but they're the boundaries, so they get the soft brackets or the parentheses. Lastly, Nick Drake. Nick Drake is out here at 60. So he definitely likes everything between 40 and 60. We're moving toward his ideal point. We're moving up his utility mountain toward his peak, toward his ideal point in terms of utility. And 40 to 60 is 20, so I go 20 in the other direction, and we just barely make it into the issue space at 80, and this is a typo right there, sorry. That's what I get for reusing some things. There we go, back to Nick Drake. So he strictly prefers everything between 40 and 80, but 40 and 80 are not in the preferred to set. They are the boundaries of the preferred to set. So what would a hard bracket one look like? There was one in the example. So let me just real quick add one more person here, just to show when you would get a case of a hard bracket. I'm going to add somebody out here at 70. So this isn't part of the problem I posted. I'm just showing you real quick what it would look like. And let's say this is, I don't know, Leonard Cohen. These are all like singer-songwriter names. So we got to be consistent, and we'll make Leonard Cohen the next person. So let me ungroup this so I can make his preferred to set the right way. So definitely he prefers everything between 40 and 70. So that's a distance of 30. So let me pull this out to just about 40 right there. And then if the issue space kept going, he would go 30 in the other direction. But this is a bounded space. It only goes to 80. So as far as I can go for him is 80. All right. So the preferred to set for Leonard Cohen starts at 40, soft bracket, but it ends at 80. But 80 is only 10 away from his ideal point. He strictly prefers 80 to 40. So I need to indicate that it is in the preferred to set, right? He would vote for 80 over 40 every day of the week. So the hard bracket here indicates that he strictly prefers 80 to 40, but it is the edge of his preferred to set because we just ran out of room. We ran out of real estate, okay? Now again, that wasn't part of this problem, but I just wanted to take an aside and show you a case with the hard bracket. And there's several in the screencast for the chapter also. All right, so let's get rid of Leonard Cohen here. He was just on the side. Sorry, Lenny. And go back to the problem at hand with the 5 voters, David Bazan, Patty Griffin, Elliott Smith, Phoebe Bridgers, and Nick Drake. And here are their preferred to sets. So the next part of the question is to find the win sets. One of them is the majority rule win set, And then I also ask you, I believe, to find the unanimity win set, unanimity rule win set. All right. So let's first find the majority rule win set. All right. So majority rule, pairwise majority rule. So I'm looking for all the alternatives that if they went one-on-one with SQ, they would win. I want to know all of those. I want to know that set of alternatives. Okay. So I have 5 people. So how many do I need to make a majority? Simple majority. This isn't a fancy K majority, super majority. No, it's just plain old one that we know and love, majority rule. All right. So we have 5 people. So to figure that out, and most of us just do this intuitively, but here are the steps. If you need a little algorithm for when there's bigger numbers than 5 voters, you just cut the number in half. So 1/2 of 5 is 2.5. And then I round up to the next integer and I get 3. So I need 3 voters to agree to beat the status quo. So I want to look for the set of all alternatives that at least 3 people prefer to the status quo. It could be more, but it has to be at least 3. Okay? So I can see here that everything between 40 and 50 has 1, 2, 3 people who prefer it. But when I cross over onto 50, once I get to 50, 50 no longer has 3 people who strictly prefer it. Phoebe Bridgers strictly prefers 50 to 40. Nick Drake strictly prefers 50 to 40. But Elliott Smith does not strictly prefer 50 to 40. He is indifferent. So we don't know what he would do if it came to a vote. And we're looking for the things that would definitely win in majority rule. It's called the win set, the set of things that would win for majority rule. So the majority rule win set is everything between 40 and 50, all right? But not 40. 40 doesn't beat itself, and not 50 because we're not really sure what Elliott Smith would do. So we write that this way. The win set, and here, because I have 2 different win sets, I'm writing the majority rule win set of 40, or I could write SQ here, is everything between 40 and 50, not including 40 and not including 50. And it will often be, for single dimensional models, the win set will often be one of the voters' preferred to set. It just happens that way. Not always, actually, but for almost all the examples we're going to see, that's how it works. All right. So, and then now let me do the unanimity rule win set. So the unanimity rule win set is what are the set of alternatives that everyone prefers to the status quo? That if we offered up this alternative against 40, everyone would vote yes. All right. So what I need to see is 5 out of 5 preferred to sets overlapping. All right. Notice there's no such alternative anywhere in the space. Over here, nobody prefers it. Between 10 and looks like 30, one person prefers those things. Between 30 and 40, 2 people prefer those. And then on the other side here, we already know between 40 and 50, 3 people prefer those. Between 50 and 60, 2 people prefer those. Between 60 and 80, 1 person prefers it. There's nowhere that all 5 prefer the same thing. So you can just imagine, what would it need to look like for me to have a unanimity rule win set for single dimension? Well, everybody's got to be on the left or the right of the status quo. That's the only situation where you'll have a non-empty unanimity rule win set. And so we write it this way. The unanimity rule win set of 40, or SQ, we could write because it's labeled SQ, is empty set. All right, is the empty set. One thing I'll caution you on, when you're writing the majority rule win set, don't say the majority rule win set is Elliott Smith's preferred to set. Write it out that it's 40 to 50. All right. It's often the case that it corresponds, but it's not always the case. So you don't want to rely on writing it that way. You just want to write the set out like this. Okay. All right, so the only other thing with the single dimensional model, let me see. Oh, no, I asked you if someone could propose something. So let's see, who do we want to propose? Let's say, let's make it, well, I'll do a couple different. I'll do two different people. Let me do three, because there's kind of three situations here. First, let's make it David Bazan, right? He gets to be the proposer. He's going to propose one thing to face 40. They're going to vote, and it's over. Single shot, single round voting game, okay? So if you're David Bazan, 40, pretty far from your ideal point of 25. There's lots of things you prefer to 40, right? You wish you could get something closer, and you're called on to propose something. What would you propose? Well, he's going to propose the closest thing to his ideal point that is in the win set. And we'll go with majority rule here, because that's the question on the homework is about proposing under majority rule. All right. So he surveys the lay of the land here. We've said they all have complete and perfect information. He knows where everybody is. He knows what they prefer. He knows the preferred two sets. He even knows the win set. All right. Of course, in the real world, we kind of intuit these things. It's not quite as precise here, but in a theoretical model, we can be super precise. So David Bazan says, all right, I want something this side of 40. What on this side of 40 will pass? And he looks at the win set and he goes, nothing. There's nothing I can propose. So maybe he would just propose his ideal just for some sort of expressive value or something, but there's not really anything he can do. So if I ask that question, you could say he'll propose 40, or not 40, I'm sorry, he'll propose 25, but it will fail, right? There's nothing he can do. He is in the minority with regards to the status quo in this group. Now let's look at Elliott Smith. All right, so Elliott Smith, what if he is the one who's called on to be the proposer? All right, they say, all right, Elliott, you're going to propose one thing to face 40. We're going to vote, and it's going to be over. That's it. That'll be what we do. So Elliott says, all right, I want the closest thing to my ideal point of 45 that will pass. Hey, I'm in luck. Check it out. 45 is in the win set. So I'm going to propose 45. They're going to vote under majority rule. Elliott Smith, Phoebe Bridgers, and Nick Drake are all going to vote yes for 45. David Bazan and Phoebe Bridgers are going to vote, Patty Griffin. Sorry. David Bazan and Patty Griffin are going to vote no. We like 40. We like the status quo. And it's going to pass. 3 against 2. It's in the win set. By definition, it passes. All right. Last scenario here, Nick Drake. What if Nick Drake is called on to be the one proposer who gets to propose the one alternative to face the status quo? And they're going to vote, and it's over. So they say, all right, Nick, what do you want? What are you going to propose? Well, ideally, he wants 60, right? But if he proposes 60, it's going to lose. It is not in the win set. So being strategic and having all the information, he says, I want the closest thing to my ideal point that will pass. So he says, all right, I'm going this direction. None of this will pass. None of this will pass. None of this will pass. All right, wait a minute. Maybe 50. Will 50 pass? Actually, 50 won't pass. 50 is not in the win set. So he'll go 49.9 repeating, all right? And depending on how accurate his understanding is of the actual policy situation, maybe he goes even further in just to make sure it passes. But for the purpose of these models, you can say 49.9 repeating. That's in the win set. It'll pass. That's the best he can do. It gives him way more utility than 40. It is closer to his ideal point, but it's not his ideal point. He can't get what he really, really wants, but he can do better than 40. So that's 3 examples of the one-shot, one-round voting game. And then the last one I gave you is, what if there's a million rounds of people proposing and they vote, propose, vote, propose, vote. So that's like that long example I gave in the slides and in the screencast with, was it Florian, Brittany, Frankie, who else was in there? Aaron, and I forget who the last person was. There's, I think I had 5 in there. So remember, that example was just an extended example to demonstrate the median voter theorem. If everyone has single peaked preference, single peaked and symmetric preferences, complete and transitive, of course, that's always there. So if everyone has complete, transitive, single peaked, symmetric preferences, and it's a single issue dimension, we know that there is a Condorcet winner. All right. We know that under pairwise majority rule, there is an alternative that if they got there, it would never be defeated. Okay. So what is that point? It's the ideal point of the median voter. Here, that's Elliott Smith, right? We have 2 people on his left and 2 people on his right. So Elliott Smith is the median voter. So for that sort of question, all you have to say, you don't have to go through 100 different rounds and show me how we end up there. All right. You don't even have to do it on the homework, although it's probably not a bad exercise to walk through if you're still not seeing why we end up there. All right. Let people keep proposing and voting. Roll die. Roll. Can there be a 5-sided die? I don't know, but use a random number generator drawing uniformly from a 1 to 5 distribution. All right, drawing integers from a 1 to 5 distribution, and let them propose. And what you'll see is you're going to end up, eventually, you'll end up at Elliott Smith's ideal point. It'll come his turn, and the win set will contain, of whatever status quo you're on, will contain his ideal. He'll propose it. It will pass. That's it. Game over. Because at that point, he has an empty preferred to set. And you need 3 out of 2. All right. So that's sort of the logic of the median voter theorem. So if you were to answer this question, you can just say, by the median voter theorem, because everyone has, what is it? Transitive, complete, single peaked, symmetric preferences, and we have 1 issue dimension. By the median voter theorem, the ideal point of the median voter cannot be defeated in pairwise majority rule. It's a Condorcet winner, and that will be the outcome of 10,000 rounds of voting or whatever it is. Okay, I'm going to breathe for a second. I'm going to get a little bit of tea here and see if anyone has questions on the single dimensional stuff. It always bugs me when I zoom up and things are slightly off. There we go. A little bit better. Okay, no questions on the single dimensional. I'm going to move to the 2-dimensional model. So first I need to add 1 slide here. Get rid of these. In fact, I'm going to put these in opposite order. Do this one first. Okay. All right. So here is a set of voters in a 2-dimensional space. All right. So lots and lots of real world policy issues are not single dimensional. There's not a way that everyone agrees we're going from 0 to 100% or something like that. Most issues I would claim are multidimensional. That's why I don't think the median voter theorem is all that useful of a heuristic in lots and lots of real politics, because there's just more going on in terms of the dimensionality. And as I showed you in the screencast, once you go from 1 to 2 dimensions, almost everything changes in terms of the types of equilibria that you get in the models. All right. So in any event, there's 2 dimensions here. We're going to assume still, though, that everyone has complete, transitive, single peaks, and symmetric preferences. And the symmetric one now is not just a mathematical convenience. It has meaning here. Symmetric preferences mean that for voter C here, moving this way affects him the same as moving this way. So in other words, he considers these two dimensions to be equal to him. And we know in the real world, people have strong feelings about certain issue dimensions, right? Say economics versus social policy, right? Some people care a great deal about one, and yeah, they have preferences about the other, but it's not their biggest thing to worry about, all right? So we're implicitly assuming with symmetric preferences that movements away from their ideal point in any direction lower their utility by the same rate, okay? And again, in more advanced models and some of the computer models that I do, I, of course, relax that because there's just so many situations where that's not a very useful model. It hides a lot of things that are very important about what we see in real politics. But for us in this class, we're just trying to get the basics down here. So we're going to stick with the single peaked symmetric preferences, which means indifference curves are going to be circles for us here. But before we even get to indifference curves, let's see, let me look at the assignment real quick. So I address all of the issues. I first draw the preferred two sets of all the members. Oh, I shouldn't have gotten rid of all those. All right. Then demonstrate there are bargains between two of the members and then draw the preferred set. Okay, so let me bring back all those preferred two sets right here. So the preferred two sets are going to be centered. I had it where they would come in all nice. So here's person A. Notice the preferred two set, because he has single peaked and symmetric preferences, they are circles, right? His utility function is either like a cone coming right out of the screen with a peak right at that ideal point, or it's that kind of dome. Either way, this represents the max on that utility dimension, which again is coming right out of the screen at him. We are looking straight down on top of his utility function, all right? And what we've done is we've drawn a circle for all of the combinations of dimension 1 and dimension 2 that give him the same utility as the status quo. In other words, his indifference curve. It shows all of the alternatives that he is indifferent between those and SQ, all right? Now, if this is truly the end of the issue space, then I would cut off these alternatives because they would be impossible. But I've gone ahead and drawn them in here as a circle. You can do that too on the homework, whether you're drawing this with some sort of drawing program or you're drawing it with by hand. Like I used to have students who would bring in like a compass, you know, like old school drawing compass. A little tip, if you're using something like Keynote, I don't know what the hotkeys are on PowerPoint, but so I can take a circle like this. Let's say I just bring up a circle from the shapes here, and I make it, I give it a line with some thickness and no fill, so it's transparent in the middle. I can line it up right over the ideal point, and then if I hold down, what is it, Option Shift, I can pull it out right from the center. It'll stay centered right over the status quo. So it makes it easy to draw these in something like Keynote. Certainly, that's what I'm using. And I think there's an equivalent way of stretching things from the center while keeping the proportions in PowerPoint. I just don't know those hotkeys off the top of my head. So in any event, here is person A's preferred two set for the status quo. Person B, they're further away. So notice their indifference curve. Oh, and one thing I forgot to say, so where is person A's preferred two set? It's everything, all the alternatives inside of his indifference curve, all right? Everything strictly inside his indifference curve. The indifference curve are not in the preferred two set. We don't know what he would do if he had to vote between, say, this alternative and the status quo. He's indifferent. But everything strictly inside, we do know what he would do. He would vote yes over the status quo. The other way to say that is that thing would be closer to his ideal point than would be the status quo. And again, we're just using plain old Cartesian distance between 2 points on a plane. All right. Now for person B, here is his indifference curve of the status quo. Person C, here is her indifference curve for the status quo. Person E, here is their, D, here is their indifference curve and preferred to set of the status quo. And then for person E, this is the indifference curve, and inside of it is the preferred to set for the status quo for person E. All right. Any questions on drawing the preferred to sets for voters in a two-dimensional issue model? All right. So the next thing I ask you to do is, it was something about demonstrate there are bargains. I say other bargains. There's no, because there's a proposal. And I've got the, let me call this P for proposal to make it match up. Should have done that. Oh, should have done that before. P, this is the proposal. Okay. So let me bring all those back in. All right. Here is this. And so I say, take two of the people and tell me, demonstrate that there are things that would make them better off than the proposal. So I'm going to jump out here so I can color their indifference curves. I'm going to do it for person A and B. All right. So I'm going to make person A, it doesn't work. Person A, bright red here. I'm going to make person B, blue here. Did it work? Yes. All right. So let me go back. Bring it back in. Here is person A and B. And what I'm saying is, so say this was a bargain that they agreed on. Hey, let's agree to compromise and do P instead of whatever it is we were doing before. So the way to show that there are things that make them both better off is to look at where both of their ideal points, both of their preferred to sets overlap. And it's this lens right here. Everything inside of that lens, A and B prefer strictly to the proposal. All right. So there's lots of things that they would both be able to say, hey, we agreed on P, but I've got to be an even better deal that we would both like, right? They would both like this better, and they would both like this better, and they would both even like that better, and this better, right? And in fact, the set of alternatives that if the proposal was on in that set, there are no things that would make both of them better off, is a straight line between the two, all right? This is called the contract curve between each person. I didn't ask you about this, but if P was on this line, what you would see is their indifference curves would be tangent to one another, all right? And because I'm using a drawing program and not a mathematical program, I don't have time to redraw all that. But if this proposal was here and we drew B's indifference curve, A's indifference curve, you would see that there would be no overlap, all right? But in this example that we're looking at, get rid of this. In this example that we're looking at, there is an overlap, all right? They would be able to find things they prefer more than P, all right? And the next thing I ask you is to find the Pareto set. The Pareto set in a two-dimensional spatial model is the convex hull around the ideal points. Actually, So you take a string, you tie it around, and you loop around each one going around. All right, the convex hull. So let me show you what that looks like by drawing it. So, and I'll change the color in a second. This is convex hull of this group. Let me fill it with, say, yellow, make it a little less opaque so you can see it. So this is the Pareto set for this group. Any alternative inside of that set, we cannot move away from it without making someone worse off. All right? There's no way to make anyone better off without making someone worse off. And the proposal P here is an example of that. So if I drew everyone's indifference curves, and I can do that because I've already done it. If I move away from P, I am moving into some people's preferred to set. They like it better, but somebody's going to like it worse. I'm moving completely off of someone's indifference curve and going away from their ideal point. They're getting less utility. However, for every point outside of the Pareto set, there are points where I can make at least one person better off without making someone worse off. There are Pareto improving moves possible, all right, for every point outside of the Pareto set. So that is the Pareto set, all right? So for the next thing, I ask you to find the win set. And let me again rename this inline. Did I call it the proposal again? Yeah, I called it the proposal on question 3. So I'm going to rename that P. So here is a set of voters, proposal P. It's the same voters, so we have the same preferred two sets. So I ask you to find the majority rule win set. It's the same exact steps you use to find the majority rule win set in the single dimensional model. How many people do I need? All right, I got 5 people. Cut it in half, I have 2.5, round to the nearest integer. I need 3 people's preferred two sets to overlap to have a win set, all right? So where are all the places that at least 3 people's preferred two sets overlap? In the homework, you're only having to look for 2. It's a little simpler. And on an exam, it would be similar. I would try to keep it simple for you. But for this example, I wanted to make it a little complicated for me to find places where 3 preferred two sets overlap. So right here, these alternatives, 2 people prefer to P, but not 3. Out here, it's only 1 person. What about here? Again, these alternatives, only D prefers to the proposal. In this little lens here, both D and E are like, yes, I like that better. But that's still only 2 people. What about, and then of course, outside of these circles, no one prefers. So I don't even need to look at those regions. In here, we already said 2 people prefer to P. Out here, only 1, only E prefers these alternatives to P. When I go up here, I've got 2 people, person B and E, both prefer all of these alternatives in this little area to P, but not 3 people. Out here, only B prefers these things to P. In here, only, well, 2 people, C and B, right, prefer all of these alternatives in this little tulipy shape, prefer those alternatives to P. And then in this petal right here, you can see there's 1, 2, 3 people. C, B, and A all prefer these things to the proposal. And in this petal, all right, let's see, who is it? It's C, B, and E. All 3 prefer those to the proposal. So if I color those in, sorry, it shifted a little, and it should be P. I can't change that now because this is actually an image. But now you have this is the win set, the majority rule win set of the status quo. I knew there was going to be one because for almost every two-dimensional spatial model, there is always a majority rule win set. That's what is known as the chaos theorem, the McKelvey-Schofield chaos theorem. There is almost never an equilibrium using pairwise majority rule in a two-dimensional space. All right, you can always find something to beat the status quo, except for the one condition where you have radial symmetry. And I go through that in the screencast, and I'm not going to go through it here. It's such a rare condition that I can look at this and see, yep, there's a cloud of dots. Yeah, there's somebody who's sort of in the center, but if I go straight through XC, I don't hit XB. And if I go straight through XB on a ray, I don't hit XD. Same thing here. If I go straight through XC, I don't hit anything, other voter. And if I go straight through XC with XE, I don't hit another voter. So the plot conditions are not met. I don't have radial symmetry. I should expect that every dot in the space, no matter where I draw it, when I draw all those preferred two sets and look at where three overlap, there's going to be a majority rule win set. All right. And then the last question asks you to use that fact to find a series of pairwise votes to move the status quo to a particular voter's ideal point. So let me look at what I said on the homework. So I give you their ideal points in Cartesian coordinates, and then ask if there's an equilibrium. So check for the plot conditions. If the plot conditions aren't met, then you do not have an equilibrium by the chaos theorem. All right. Then I say, suppose B has been appointed the sole agenda setter. If the status quo is at C's ideal point, can B construct an agenda to get to his ideal point? The answer is yes. If the plot conditions aren't met, yes. And then now I ask you to construct such an agenda. So a series of votes that move the status quo to a person's ideal point, all right? And then I ask you what theorem that illustrates, and I've already said it a couple times in the screencast, so I'll let you get that one. So here is a little example. Let me move the status quo to, let me change its symbol so we'll know what it is. So I'm going to make it a star. For the status quo, that. And then I'm just going to change its color. So it matches. All right, so there's the status quo. I'm going to group that back up. So let's put the status quo at person B's ideal point. Got to use something to get it right there. Okay, so person B's ideal point is the status quo. All right, and I want to construct a series of votes, right? And so for you, that will have a coordinate, right? You'll have a particular coordinate. For you, you're starting at status quo is at C's ideal point. So you're starting at 2, 2. So you're going to have numbers for this. I'm just going to show you the logic of how to find it, all right? So I want to get to, let's say, C's ideal point. Let's say this is the goal here, to get it to person C's ideal. So I'm going to make that green just so we know what we're shooting at. We're trying to get to here from here. And I need to propose a series of votes. So propose something, it wins. Propose something else, it wins. Person C is getting to decide what faces the new status quo each round. It's a sequential voting game, okay? So you could start right here and draw everybody's preferred two sets and find the win set. And then person C could say, let me pick something in that win set that's close to me. And it would pass, it would become the status quo number 2, and you could redraw everything, right? Takes a lot of time to do that. And we don't really care so much about any one particular round. We're just trying to construct the agenda. So in the last screencast, I showed you something called the cut point method. The cut point method tells you, and let me bring back, well, I'm gonna just have to generate a new one, how to determine between two things what will pass. So let's say this, I wish you could just change the shape, but you can't. This is the proposal. Right here. Let's make these some other color, like orange. That's text. There we go. Not the same orange. It'll drive me crazy. Okay. Oh, it didn't work. Oh well. Okay, they're both orange. You get it. So how can I tell if this proposal will beat the status quo? Well, I could draw the preferred two sets, find the win set, but there's a shortcut that will make finding this agenda a lot easier. All right. So to find the cut line, you draw a straight line between the two alternatives, right? Go halfway between them. You'll have to use your little midpoint formula. Then draw a perpendicular line through the space at the midpoint. So get this just about right. That looks pretty 90 degrees to me. So would this proposal beat the status quo? C and A and B are going to vote for the status quo. E and D are going to vote for the proposal. So this would be a bad first step for person C, all right, in terms of getting the status quo all the way here, because that one just failed. So maybe he tries my ideal point. Let's shoot for that. Let's do that. Let me try my ideal point. So draw a straight line between the two proposals that you're analyzing. Find the midpoint. And draw a perpendicular line to the original line at the midpoint, going all the way through the space. That's not quite perpendicular, is it? About there. All right, so there's a perpendicular line. So 1, 2, 3 people will vote for it. It will pass. Person C would have a really easy job here, all right, if this was that situation, all right? So I can't remember. I think you're going to have to do several rounds in order to get the status quo to the person's ideal point in the homework, all right? But basically, you would propose something, it would pass, usually 3-2, sometimes 4-2, rarely 5, sorry, usually 3-2, sometimes 4-1. Rarely is there going to be unanimity. Sometimes there is. Everybody on one side of the cut line, right? Propose it, it passes, and then that becomes the status quo. Next round, what is XC going to propose, right? One trick I'll tell you, since those of you who joined on the screencast, is if you can't get their ideal point the very first go, don't go toward their ideal point. Go way away. Find something that's pretty far away that will still beat the status quo. Then it gets easier, weirdly enough, to pull it back in toward their ideal point. You've got to blow everybody's preferred two sets way up so that you can get XC inside the win set, is the logic of that, right? Because the further away the thing they're considering is, the new status quo is, the bigger their preferred two sets get, right? And so that makes it easier to then pull it back in. So that's just a little trick I've learned from doing these things a million times. All right, so that's it. I've gone a little bit over time, but I'll still stop and ask for questions. And maybe those of you watching on YouTube can just watch this at double speed or something to get it under an hour. And I apologize to those of you live. We still have somebody here with us. Yes, okay. Any questions from those who are live?
Are you gonna post the PowerPoint that you just did?
Yeah, I can, but again, like I edited things as I went, but I'll be happy to post this final thing here. Yeah. So let me save it and export it to PDF so everybody can view it. Obviously, not everybody has Keynote. And let me put it in the correct folder. But yeah, I'll definitely do that. I think this is where I had this example living. I did not. Anyways, I know where it is now, and I will post this right underneath the Zoom, the link for the Zoom once I get it. It takes forever to save it, to compile it, then I have to upload it to YouTube, and then YouTube has to compress it. So it takes, almost close to an hour to do all those steps, but mostly it's computer work, not me. Any other questions? All right, so hopefully you have several examples now, both in the screencast, here in these examples, and in the book to work on these. And I've extended the deadline, of course, till Sunday. I'm available almost all day tomorrow to answer questions either by Zoom or email, Skype, FaceTime, telephone, whatever. I can do any of those things. Let's see, let me stop share. And so I'm happy to do that. Saturday, I won't be very available. I'll try to check email, but I'm going to be in Athens. So all I'll have is my phone. And I'll try to remember to take a laptop just in case. It's always nice to have the ability to pull out the laptop and have all the slides there. But I won't be quite as available on Saturday. Sunday, though, I should be back here in Macon. I'm not staying overnight in Athens. I should be available to answer questions then also. This was really the time to ensure if you had questions to ask them, but I'm sure people will have additional ones. And so I'm happy to be available. Just let me know. All right, everybody. Good seeing you, quote unquote. And let me know if you have questions. By the way, this is the big stuff. It gets easier from here. Right? We kind of built up and then we hit this big hill of absorbing all this material. And then we're just going to use it for the next week as a way of thinking through not just majority rule and unanimity rule, but the properties of other types of voting rules in terms of causing things to be moved toward the middle or causing things to move to be more polarized. And that's very timely in our current political landscape. All right, that's it. See you guys.